Hi, my name is Dr. Phil Appleton at IPAC Caltech, and I want to talk to you about some new images. The image of Stephan's quintet that was just released by the James Webb Space Telescope. I've been working on this system for about 18 years. So we started first with the Spitzer Space Telescope, which is in some ways the forerunner of the JWST, a very powerful telescope in its own way. Okay, so what we're seeing here, it's a composite of different colors that represent the different bands that are observed. And the most important thing that you see in the image are these diffuse objects, which are galaxies. And this is called a compact group of galaxies. And you have a very big one here, and then there are two here, and another one down here, and this is the fifth one, and that's why it's called Stephan's quintet. When the quintet was first discovered at the end of the 1800s by a guy called Stephan, it was not known that these systems were like giant, that these blobs essentially that he saw in his images were entire Milky Way systems. And what's fascinating about Stephan's quintet is that all these galaxies are crunched together in a very small area of space. If you imagine our own Milky Way system, which is a giant pinwheel of rotating gas and dust, the nearest galaxy to us is the Andromeda galaxy, which is a faint fuzz in our own sky when we look up there. But the Stephan's quintet would, if you imagine this is our own Milky Way system, these galaxies are very, very close, within almost 1/10 of the distance between our own Milky Way and the Andromeda. So these galaxies are very, very close together. And as a result of that, they tend to be smashing into each other and colliding and producing what we call tides. I mean, just like you have tides on the Earth, except that in galaxies, tides cause these long tails to be produced when galaxies pass by each other very closely. And this is a beautiful example of that. You can see this long tail here. And this is a tail of stars that are being strung out and gas caused by this, due to this galaxy colliding with one of these in the past. We don't know exactly which one. What's interesting about this is there's another galaxy here, which is not part really of the physical association of these galaxies. This one is much, much closer to us. These are far, far away in comparison with this one. But I'd like to show you now another image that was taken in the past. So this is an image of the same region. And this time it was taken with Hubble, the Hubble Space Telescope, in the visible light. And the background image here, you can see the same galaxies in there. Here's the foreground object. Here's the galaxy that had the long tidal tail. And superimposed on this picture, which is mainly showing you stars and a little bit of dust, is an observation that was made by my team on using the Spitzer Space Telescope. And it was able to detect this structure across the center of the system. And what is the nature of this structure? We believe that these are molecules of gas, molecular hydrogen, that are emitting infrared radiation. And so Spitzer was able to see the infrared radiation, and in the background you see the stellar emission mainly from stars. And what this told us is something very strange going on here. And what we believe is happening is that this galaxy here is actually flying into the group. It's colliding at a tremendously high velocity, smashing into the gas that surrounds the galaxies and is producing an enormous shock wave in front of this galaxy. And the shock wave is producing little clumps of stars along the shock front. And if I go back now to the JWST image, what's amazing about this now is that we can actually observe the molecules in great detail. And that's what we're seeing along here. And if we zoom in on this, you can see all these molecular structures along this shock front. When those clouds are compressed, they collapse And in fact, it's a sort of battle between the shock wave, which is driving energy into the gas, and then the gas's ability to collapse to form stars. And in fact, star clusters are appearing also in here along the shock front. And here's another image from JWST where we can zoom in again on that same region, but now we're seeing purely stars, and in particular infrared emitting stars. So these are star clusters that are usually very young. And you can see up here, for example, there's lots of little speckles and things that are basically the result of the beginnings of star formation, where stars are hidden inside their little dust clouds, and they're starting to emerge from the dust clouds and form stars. And so there's a battle going on between the energy pumped in to the gas from the shock wave and the gravity, which is trying to form stars. And so we've got this tremendous battle going along here. And that's what makes it interesting to us, because we're trying to understand how stars form in very turbulent environments, which is what we're seeing here. One critical question that astronomers have always tried to understand is why star formation is quite inefficient. Why is it that there's lots of gas in the universe, but the star formation that occurs in the universe is very inefficient? And so by understanding this system here, we can understand the physics of the astrophysics of how the stars are being born in a highly disturbed and turbulent and stirred up environment. And then we can apply those kinds of ideas to looking at the early universe, where we think that such things, galaxies collapse out of gas, shock waves and turbulence are definitely a major factor in the formation of galaxies. So it helps us understand how galaxies formed in the first place. And we're using this as a sort of local test bed to try to understand the basic underlying physics of it.